All right. Well, here we are. It is 10 o'clock, so let's get started. Thanks for coming. What we'll be talking about in this particular section is adapting your network code over to IPv6. And for those of you who don't get the comment, that's home in IPv6 speak. So it is the 127.001 equivalent. We'll get into that. So we'll talk a little bit about IPv6 history, why bother converting to IPv6, what's the addressing scheme, and how do we coexist between IPv6 and IPv4. We'll look at some of the more common configuration commands, things that you should know about when you're trying to configure an IPv6 system. And we'll go into some detail on server-client code flow and what it looks like in IPv4 and what it looks like in IPv6. We'll finish talking a little bit about how we go about planning the transition from IPv4 to IPv6. And we'll finish up with a quick summary. So unlike yesterday's presentation where there were no words, this presentation has a lot of words on the charts. So let's, starting a little bit with the IPv6 history. Back in the 1990s, the Internet Engineering Task Force took a look at the current usage rate of the IPv4 address space and said, you know, it seemed like it was going to be big enough back when we started this in the 1960s, but gosh, no, we're going to run out. The original IP system was built as a mechanism for the military to do away with telex systems. So they were basically designed with the idea that you were going to have a network for the Army, one for the Marines, one for the Air Force, the Army, one for the DoD. Okay, that's 6 or 7, and that should surely be enough. What they did was they then expanded that out a little bit for universities to do some research. And as the university grads got used to using this internet to send out emails and say, hey, kegger tonight at my house, and everybody go, hey, that's really cool, we should have that. I remember quite well using the intranet, the ARPANET at the time, as a mechanism for communication, and it was just email traffic, and it was just government or educational institutions. And when they talked about creating an internet that would then be available to commercial entities, everyone was shocked, stunned, and amazed. It's like, oh, this can't possibly work. People can't figure out what it does. You know, this is not going to fly. But suddenly we then had Mosaic come out, and that started the whole treadmill of Web 1.0, Web 2.0, etc. In 1998, the Internet Engineering Task Force actually finalized the concept that was originally put out as IPNG. This was actually a play, IP, the Next Generation, because at the time there was a new show on television called Star Trek, The Next Generation. So they figured, hey, okay, we'll call it IP, the Next Generation. That'll be a great idea. This came out and was finalized in RFC 2460 as IPv6. There actually was an IPv5. It was an experimental network. It never really got deployed in any large sense, but there was one. So if you ask, well, what happened to IPv5? There really was one. They just didn't actually deploy it anywhere. So some of the issues that we run into with IPv4, of course, is that it's a 32-bit address space. And that certainly seemed like enough at the time. As we started expanding the internet, we then went from a Class A address, which was the first octet was the network, the remaining 3 octets were the host, to a Class B, a Class C. Eventually there's a Class D, a Class E, and a Class F network that was designed. Getting down to the case where you would have only 1 or 2 hosts and all the rest of it would be network. Now, because we started running out, and people noticed that we were running out as soon as websites really started getting going. So they said, look, the solution for this is we have got to develop this new protocol, IPv6, but it's going to take a little while for us to be able to deploy it. So let's come up with a mechanism to slow down the expansion of the IP address space and give us some breathing room. So they introduced this thing called CIDR, or Classless Internet Domain Registrations. And with a CIDR address, it basically gave us the ability to take the address space and further slice and dice it so that we could then incorporate these things called network address translation boxes, or NAT boxes. The idea with the NAT box was you would hide behind the NAT box. You would then be able to set up an unroutable class address, either 192.168 or a 172.16 or a 10.0 address. And when you would have these unroutable addresses, you would then go to the NAT box. The NAT box would then act as a proxy that would then put your information out on the internet for you. The problem with NAT boxes are they're stateful. They have to keep track of every single ingoing and outgoing connection, and they then have to be able to reassociate a particular port address and IP address on the outside with an inside IP and port address. So they have to keep track of a lot of traffic going back and forth. And this really becomes their Achilles heel, because it adds considerable latency to the network. And as we see right now, the characteristics of the current IPv4 internet is that it's a jumble of these things. We've got NAT boxes and firewalls and load balancers. There has been a huge market that has been created around trying to stretch this IPv4 address space as far as possible. It's today almost impossible to get direct access to a device on the internet. There's almost always some middleware box in the way. Now, that could be either a bug or a feature, depending on how you look at it. Because on the plus side, if there's always a box in the way, it means that nobody can get into your system and hack it directly. They've got to go through a NAT box or some other transit mechanism. On the other hand, it also means that you've just introduced a considerable amount of latency. And if you'll remember from my talk yesterday, 29% of all internet traffic last year was Netflix. So every time it transits a NAT box, you're adding latency to the system. And of course, people don't like latency in their videos. So we have to come up with a way of trying to address that at some point. It really requires the NAT box. It has to frequently rewrite addresses on packets as they transit through the NAT box. So the NAT box becomes a choke point. So why bother switching to IPv6 at this point? I mean, when you think about it, IPv6 was put out as an RFC in 1998. Why has it taken so many years to get to the point where we really have to consider using it? The answer is, frankly, we're out of IPv4 addresses. That's really what it boils down to. And because many people, CIOs and others, saw this coming, the CIO of the Army, CIO of the Air Force, of course, most of the U.S. government chief information officers, and not only U.S. but foreign government have seen this exhaustion of the IPv4 address space coming for quite some time. They've actually now mandated the use of IPv6. So in spite of the fact that we might be able to stretch the IPv4 address space a little bit further, the reality is that it's now being mandated by most of the major governments. So we probably can't continue to ignore this problem forever. We do want to regain some end-to-end transparency as well. And that is because of the changing nature of how people are engaging in entertainment. Certainly the broadcast television people are quite concerned that viewership of broadcast television has dropped precipitously over the last few years. Now, they are in fact taking considerable steps to make sure that their broadcast television series, like American Idol and those, are automatically then available on Hulu and other such services that are subscription services, so that they can in fact get their message out there, get their advertising out there, get their product paid for without necessarily you watching it live when it's broadcast. So end-to-end transparency of streaming media starts to become a huge factor in all of this. Another piece of this puzzle is that when you take a look at the core gateways, and this is a much more subtle thing, the core gateways are tremendously overburdened at this point by address bloat. There's so many address CIDR mechanisms and everything in place that the core gateway address tables are huge. And it's taking a long time for the core gateways to actually be able to look and address up to forward packets. So that's another problem. And of course, IPv4 as a protocol, we'll see here in a moment, is a pretty complex protocol which takes a lot of processing in order to take a look at it. Kind of the last thing, of course, is the ever-present specter of security. We all want to make sure that nobody's looking at our packets. We want to guarantee that the packets got there in one piece, that they hadn't been modified. We also want to add non-repudiation. We want to be able to guarantee that the guy who sent me the packet can't deny that he sent me the packet. All those characteristics come into play with IPv6. And IPv6 adds to it an actual security layer called IPsec. Now, IPsec has its own AES encryption built into it. The thing about IPsec is that it's only as secure as the people who deploy it. The big problem with IPsec is that right now only about 12% of IPv6 installations are actually using IPsec. And that's because they claim it's, well, it's encryption, it takes keys and certificates, and oh, gee, that's a lot of work. I'll get IPv6 up and running first, and then I'll get around to adding the security to it. Maybe sometime, someday, maybe never. But the protocol, that's not the protocol's fault. The mechanism is there in the protocol. It's just people, IT managers, et cetera, haven't taken the step to actually implement all the features. And so, yes, sure enough, last April, we in fact did run out of internet addresses. This was a snapshot that I took back in April. Number of IPv4 addresses, 0. So we're out of IPv4. It turns out Asia ran out of IPv4 a couple of years ago. And it's just because since the US was the place where the ARPANET started, the US had more addresses, more address space than anybody else. And it just took us a little longer to exhaust it. But now, in all the regional internet registries, basically all the IPv4 address space is gone. Now, because the IPv4 address space ran out back in April, did the internet stop? No, it kept going. And that is, of course, a key that says, look, yes, this is a problem. We've run out of address spaces, but the whole thing doesn't come crashing down. There was no, Y2K kind of issue where, oh, everything's going to stop because we run out of internet addresses. No, the existing system will continue to work for quite some time. In fact, they're anticipating that we'll probably have about another 20 years of screwing around with IPv4 addresses before they finally become so minimal that they will just simply say, hey, look, we're stopping IPv4. That actually happened, by the way. There was a network control protocol, NCP, that was actually the predecessor to TCP. And in, I think it was 1981, they said on one day, that's it, off. They turned it off and everybody switched. There might be something like that year 2020, 2025, maybe when the number of seconds wraps around in the epoch. That's a 2038, okay. Maybe by then we'll have it, I don't know. But certainly they're claiming that IPv4 probably has about another 20 years before we see it disappear. And the reality is because we're so used to hiding behind NAT boxes, IPv4 can continue to exist inside of the enterprise for a long, long time. As long as you're behind a NAT firewall of some sort, you don't actually see the IPv6 addresses on the outside world. You can use IPv4, the firewall will handle the translation, you can do tunneling, there's all kinds of games that you can play. So the reality is that we have to think in terms of a dual stack solution for the foreseeable future. That is, probably for the next 10 to 20 years, we're going to have to be dealing with dual stack. So I said that IPv6 is a simpler protocol. If we take a look at IPv4 here, we see the version and the header length and services points and total lengths and identification fields and time to lives and protocols, source and destination IPs, and then we could potentially have up to 5 options inside of the header. So part of the problem with IPv4 was that we never really knew how big the IP header was going to be until after we received the packet. And we would then have potentially to decode additional option packets there in the header before we could even consider looking at the payload. So this is a fairly significant overhead for any processor, certainly if we start taking a look at smaller processors like the Cortex-M0 and Cortex-M3. So one of the things that they've done with IPv6 is they've tried to simplify it. So now we have the version, so that's still there, traffic class and flow labels, but this is much simpler to decode because for the most part, most of the actual people that are doing, or actual machines that are doing packets, really don't have to do much with this stuff. They're really looking at the source and destination addresses. And the hop limit here is no longer a time in seconds as time to live was. It's now an actual number of hops before the packet gets dropped. So the original TTL actually got reinterpreted by many machines and many protocol stacks to be a number of hops. They just simply acknowledged that in IPv6 and said it's not a time to live, it's a hop count. And when you get down to a hop count of 1, that's the end. It's not going to go any further than that. If you're not already on your destination network by that time, packet gets dropped. So you'll notice 2 big things about this particular packet, the source address and the destination address. Those are the 2 big things that exist inside of this protocol header. And therein lies the interesting problem, because with IPv6, they wanted to guarantee that they weren't going to have an IPv7. They wanted to guarantee that there would be enough address space that we would effectively always be able to live with IPv6 forever. Now, forever is a long time, but nonetheless, as those of you who were in the keynote yesterday, I showed you how many addresses there are. Think about every man, woman, and child basically having a couple of hundred networks assigned to them. Effectively, when you're born, they won't give you a Social Security number anymore. They'll just simply tattoo an IP address to your forehead. And that will be your address that you'll carry around forever. No more telephone numbers, no more Social Security numbers, no more passport numbers. Your IP address will be, no, I'm just kidding. But that's an interesting concept. You would always be addressable at that point, I guess. The question is, would you be routable? Different issue. So special addresses in IPv6, of course, we have : : 1, that's the loopback address, and : : that is otherwise known as the default address. So in IPv4 speak, we have this address called default. It's 0.0.0.0, otherwise known in socket speak as inadd or any. This is the IPv6 equivalent of inadd or any. Now, when you look at these addresses, there's another thing that's missing here. Of course, remember that IPv4 has a broadcast address. Send it to all Fs. IPv6 doesn't. There is no broadcast address in IPv6. There's a multicast address, and you can have multicast groups, but there is no broadcast address. So it does change fundamentally some of the concepts for being able to handle things like ARP, where we would then basically broadcast to everybody and say, hey, does anybody know who I am? Or who this address is. So addressing and the ability to do address resolution, name resolution to address resolution, becomes a significant problem in IPv6, and we'll take a closer look at that as we go through. Now, when we talk about a standard IPv6 machine, say a Linux machine, we have an Ethernet PHY, and this MAC address on the Ethernet is not going to change with IPv6. Ethernet stays the same with IPv6. There is a slight change in the packet in the protocol header, but that's at the IP layer, not at the MAC layer. if we take a look at this MAC address, there is something in IPv6 called a link local address. Now, a link local address is for use on the local network segment. And it's an address that's automatically assigned by the stack. So we can always spot a link local address because it'll begin with FE80 as the first set of octets. As we'll look here in IPv6, IPv6 addresses are in hex. So no more dotted quad, 128, whatever. No, that doesn't exist anymore. It's now going to be in hex. And this immediately means that the average run-of-the-mill grandmother is probably not going to be able to set up her IPv6 address, because she's going to look at it and it's going to be FE what? What's an FE? But of course, this also gives the possibility of having some really interesting addresses like Dead Beef Cafe as an IPv6 address. That's kind of a cool thing. Now, but look at what happens here. We see DC, the last octet here in the MAC address, and it matches directly. So 7626, there is an FFFE stuck in the middle of it. Then we have 0A, 26, and then we take the last, or this first octet, and we set the second bit in the first octet, and that becomes this value here. So there actually is a formula for calculating an IPv6 address from the MAC address. Now, people who are really big into privacy look at this and they go, oh my God, it means that my IP address can be directly linked to my computer by its MAC address. I cannot deny where this packet came from. This is not good. So, by the way, this is referred to as an EUI64 address. So they take the mechanism and they convert it over to EUI64 format. They stick in a couple of things here, and that's how they get their address. This is automatically done by the protocol stack. It turns out there are other ways of assigning IPv6 addresses. Notably, Slack, which is a stateless auto address configuration protocol, and of course our good friend DHCP, except they call it DHCP6. Now, in the case of Slack, it's stateless. So the thing that assigns the address doesn't keep track of the address that it was assigned, So it sends it off. Now you have an IP address, but it doesn't keep track of the association between a MAC address and an IP address. It's not stateful. DHCP6, on the other hand, can be stateless or stateful. So DHCP6 can be used to then track back to what addresses were assigned on a per MAC address basis.
So that means that several guys can get the same IP address?
No. It keeps track of the fact that the address was assigned, but not who it was assigned to. Now, there is a third technique that's used for auto-assignment of addresses, and that can be used by the routers themselves. So as you try to go out through the gateway to the internet can see that you don't have an IP address yet and automatically assign you one. So there are several different ways that we can get IP addresses. Of course, you could also statically assign an IP address if you wanted to, but that requires a lot of typing, and most of us are typing challenged, to say the least. So here's some examples of IPv6 addresses, and these are all equivalent. When we take a look at zeros inside of an IP address, those zeros can be left out if they're not significant zeros. So in this case, we have 0D here, and we can actually just drop this 0 completely and just have DB8. That's fine. That's acceptable. But we can take patterns of zeros, groups of zeros, and simply abbreviate them as : And so this : could be just that group or any number of combinations till we get to the point of we have this address, which is a real quick shorthand way of having written that address. Now, when you look at this, we have these colon separators here between the hex digits. This, of course, means that specifying an IP address and port number in the way we would normally do it for an IPv4 address, where we have 192.168.101:110, we can't use that technique anymore because the colon's now been overloaded by the actual address itself. So this is how we have to reference IPv6 addresses and port numbers on HTTP links now. So it is a little bit more complicated. We have a little square bracket sticking out there. We can then use the zero compression technique so that we don't have to type quite as much. But then we still have the colon out there but for the port number, but now it's on the outside of the square brackets. Now, when you look at addresses like this, I mean, this just screams we need to have a better way of doing this. We can't actually expect normal humans to key in addresses like this. I mean, gone are the days where I can remember that my home network segment is 192.168.101, and I can know that my printer is 101.75, et cetera, et cetera. That's probably not going to be practical as IPv6 deployment starts rolling out. So we have to have some way of being able to represent addresses as names and handle name to address resolution. Of course, the way we would do that is DNS, but there's a little trick that you have to do with DNS. It has a special type of record now called a Quad A record. And the Quad A records then provide IPv6 addresses, whereas the AAA records are IPv4 addresses. And of course, the representation of IPv6, of course, CIDR notation, the classless internet domain registration notation, is now pretty much ingrained in the way things are done. So you will, in fact, see addresses represented in CIDR format. So we'll have this address slant 48, which means I have, this is the network portion, and I have 48 bits for the host portion. Yeah? Yes. Unfortunately, as IPv6, this is one of the reasons why IPv4 is not going to go away for probably 20 years, because so many people will be reluctant to actually have a DNS server set up in their house. However, what it means is an opportunity. As I said yesterday, chaos leads to opportunity. It's an opportunity for a conveniently configurable box that becomes your next router that has built inside of it a DNS server on the local bus side that doesn't interfere with the DNS on the internet side, internet with a capital I side. So yeah, there's going to be, yeah, it's just resolving IPv6 addresses. Now, you might argue, well, hey, what about Bonjour? What about MDNS? What about rendezvous and all that sort of business? Yes, all those will continue for the foreseeable future. So there's no real crying need for you to convert to IPv6 in your house. But there's some interesting information we'll talk about here in just a moment as to what the major vendors like Google and Akamai and Yahoo are going to be doing by June the 6th of this year. So IPv4 and IPv6 will have to coexist for a long time. And fortunately, if we take a look at Windows, if we take a look at Mac OS, if we take a look at Linux, they've been dual stack for a long time. Android is actually dual stack. Very few people are aware that Android has IPv6 in it, but it does. And if you have your IPv6, if you have your Android device rooted, you can actually get out and look at the IPv6 address and dork around a little bit with it. Again, remember, Asia has been using IPv6 for a couple of years now in their cell phones. So it's just us here in the West that are a little bit behind the whole grand scheme of things, and we're just now catching up. Now, with a dual stack, we of course have both IPv6 and IPv4 resident at the same time. The network interface layer, the Ethernet layer, stays the same, so that hasn't changed at all. But now we have issues of what if our service provider doesn't service IPv6 addresses? In my particular case, I'm with Cox Communications out in Washington, D.C., and Cox Communications has publicly stated that they have a plan for transitioning to IPv6, but they haven't given me any actual dates and times yet. And a lot of that is because most of the DOCSIS modems that are being used on broadband cable don't understand what IPv6 is, and as they start to convert over to IPv6, it means there may be a whole lot of replacement being done. And of course, when you lease those modems, it means that's a cost directly to the service provider, and they're not too keen on that idea. But as I said, they're really not going to have much of a choice. That being said, there are mechanisms for being able to tunnel IPv6 across IPv4 networks. There's 6 to 4, 6 in 4. I happen to use Teredo. I'll show you an example of Teredo here in a minute. And there are also tunnel brokers. So what happens is you wrap your IPv6 traffic in IPv4 traffic using something like Teredo or 6 to 4, send it out across an IPv4 network to a tunnel broker who then strips off the IPv4 header and puts it out on the internet as IPv6. So that's happening quite a bit these days. And I happen to have a tunnel broker that I use. It's usually a free service, so it's not like it's going to cost me anything to use Teredo. But if the network gods are smiling on us, I'll show you what it looks like when you use a Teredo tunnel. Now, what about all the commands that we've come to know and love in networking? Ping, traceroute, IP tables. What do we do? How do we convert that over to IPv6? It's real easy. Just put a 6 on the end of it. Ping becomes ping 6. Traceroute becomes traceroute 6. IP tables becomes IP table 6. It's not that hard. Except that now we have to worry about the goofy 128-bit addresses now. So again, we need to make sure that we've got a good name server sitting out there someplace. And as I said, Linux, OS X, and Windows all have IPv6 support. A lot of RTOSes actually support IPv6. VxWorks does, ThreadX, QNX, all those guys already support IPv6. However, you have to ask your vendor, because manufacturers like MicroCOS, the Mucus guys, they don't support IPv6 yet. So it's going to be kind of a hit and miss sort of thing over the next several years. As we start working with individual devices of the Internet of Things, we're trying to bring all this together into one place. Some of them will support IPv6, some of them won't. So again, it drives us to this idea that we're going to have to support Dualstack in our software for quite some time. Now, what's the typical code flow for an IPv4 client and server? We have a socket connection that'll return a file descriptor that'll open up a socket. And what's a socket? Of course, it is the concept that back in the day at Berkeley, they were trying to figure out a way for doing inter-computer communications. And what was the one thing that everyone knew how to do? Open and close files. So if you take the concept of opening, closing, reading, and writing a file, and you extend that to network communications, you have the concept of a socket. Now, so the socket call itself returns a file descriptor. We can then use read and write calls on that file descriptor, just as though it were file I/O, and actually have it read and write across the network. The bind call here, this binds a local address. What do you have to have in order to open a file? You have to know its name. That's what the bind call does. It binds a name to the socket. In socket speak, a name is an IP address and a port number. So it's 6 bytes. But the reality is that that's what you're doing, is you're binding a name so that somebody else can find the socket by the same name. We use the listen call, and sockets, we're talking about stream sockets here, sockets are very much like telephone calls. You have an inbound trunk, you have a receptionist that's able to answer up to 4 telephone calls at the same time. When she or he answers the phone, they then say, oh, you want to talk to so-and-so? Let me transfer you. This is exactly what happens in the accept statement. So we listen, we advertise the number of inbound connections that we're willing to have waiting. And if we advertise 5 connections, if I have 5 machines trying to connect to me at the same time, they'll all get the equivalent of a ringing sound. The 6th one that tries to connect at that exact same time will get the equivalent of a busy signal. So when we're writing our socket code, we need to make sure that we take into account the possibility that the return from the connect call could in fact be an eConnect refused because the connection was busy, and then retry it. So these are not blocking calls. This one, however, is a blocking call. When you go into an accept statement, you're basically saying, I'm going to wait here until somebody connects to me. The return from the accept statement is a new file descriptor. So we are listening, we're basically doing the accept on, say, port 80, which is our HTTP port. When we get the connection, it will create a new port, say a port 2550, that we'll be then doing all that communications on, and that frees port 80 up so that somebody else can connect to it. That's the general flow. And of course, once we're connected, we can use read and write or receive and send. Either one of these two APIs will work just fine for TCP. In the case of UDP, we don't have the accept and listen business. We just simply start sending to and receiving from packets or receiving from hosts. On the client side, we call socket and we call connect, but you'll notice there's no bind, there's no listen, there's no accept either. That's because if we initiate a connect to a known telephone number, the telephone number we're calling doesn't need to know what phone number we're calling from. So there's no bind here. We don't need to know that. What's going to happen is the operating system will automatically assign us the next available telephone number. Now, just like in real telephone calls, there is a caller ID here. So when we get the accept, the return from the accept will also have encoded in it the IP address and port number of the initiator of the call. That also happens in the send to and receive from systems. So these guys here, we basically just have the socket and the connect, and then we can start reading and writing. So that's typical code flow in IPv4. The good news is that that's the exact same code flow in IPv6. There's no difference between IPv4 and IPv6 in the way the code flow works. The only issues that we have, of course, is the address structures are different because we're not passing 4-byte addresses, we're now passing 116-byte addresses. And, of course, any other APIs that actually expose the size of the IP address in some way have to change. Because anything that would then have a size of field basically has to be told that the size of is different. It's not the old IP, the Sockaddr in structure. It's now a Sockaddr in 6 structure. So there are some changes in the things that you pass as structures, but the function calls themselves, the connect, the bind, the socket, all those stay the same. So what are the strategies for adding IPv6 support? Well, since most of the OSs support Dualstack, one strategy is ignore the problem. It's going to be something that we have that will be around for another 20 years. If there's no crying need for you to actually speak to IPv6 devices, just ignore it. Continue to use IPv4 as you have with NAT, and the world will continue. Nothing's going to come. There's no cliff that you're going to suddenly fall off. That's one strategy. I don't necessarily recommend that strategy as a long-term viable approach, but certainly is something that you could do probably for another couple of years and get by with it just fine. You could start developing IPv6 only code. Now, that's the simplest technique, as it turns out, and I'll show you some examples here. It's really easy to convert from IPv4 to IPv6 code. Unfortunately, it then means you're in IPv6 world in a place where we're having to share with IPv4 code. So you can kind of go IPv6 and force everybody that direction, but there's still a lot of folks out there using the old protocol. So do you want to lose contact with all the people you currently communicate with? The answer is probably not. Because IPv4 is going to be around for a long time, we probably need to create some sort of IP agnostic approach to being able to handle this. So what is that? What are these techniques? One approach is it turns out that with IPv6, we can actually trick an IPv6 application into sending IPv4 addresses. So if we decided to go with the approach that says we'll do IPv6 only, we can actually put into the address this : FFFF, and then the IPv4 dotted quad. And that works. And you'll notice this is a really weird looking address, because now instead of having the colons that we would normally expect to see for an IPv6 address, we have now colons and the dotted quad. And what happens, this is called an IPv4 mapped address, as it transitions through the IPv6 stack, it then realizes that this is an IPv4 address, strips the IPv6 stuff off, and puts it out onto the network as an IPv4 packet. Tricky part about that is that now we're not really getting any advantage of the smaller headers, the easier to process packet formats and things of that sort for the IPv6. We're going back to the old technique for IPv4. So the performance drops when we do this, but it's something that would work. So it might be a transition strategy. Of course, here we have a standard IPv6 address. So we could have one application that when it figures out that it's talking to an IPv4 mechanism or an IPv4 device, simply uses an IPv4 mapped address. It's just a parsing issue. When we take a look at the packets that are coming in, the Ethernet packet header will have 0800 if it's IPv4 or 86DD if it's IPv6. So that's how, at the layer 2 layer, we can determine whether it's IPv4 or IPv6. Now, porting applications to IPv6 only is basically you find all the places that you had something that was specific to IPv4 and you put a 6 on the end of it. Again, it's a kind of a pattern that we're seeing here. So Sockaddr N becomes Sockaddr N6, AF_INET becomes INET 6, protocol family INET becomes protocol family INET 6. This works pretty well for most protocols except those protocols that actually embed the IP addresses directly in the protocol, like FTP and NTP and a few of those types of protocols. So it doesn't work for all protocols, but it would work for a generic socket kind of connection. Here's the comparison between the two protocols. We have IPv4 and IPv6 here. It turns out that these, of course, are all IPv4 specific. These are IPv6 specific. But these things that are highlighted in red are functions that work in both stacks, both IPv4 and IPv6. Now, Sockaddr has been around for a long time. Sockaddr is just a generic socket address structure. Kind of the funky thing about Sockaddr is that if you look at its specification, which I think I have here, yeah. So if we look at the Sockaddr specification down here, you'll notice that the data, which is actually the protocol address, is only 14 bytes. And IPv6 is a 16-byte address. It turns out there's a union structure inside that can be dorked around with a little bit to allow it to pass 16-byte addresses by casting it as a Sockaddr structure. I don't recommend that as a behavior because then when you look at the source code, it's really confusing as to whether you're dealing with IPv4 or IPv6. But it is one of those things that's possible because now the generic socket address is this thing called SockStorage. It's now a field that's large enough to handle any of the address families. So whether it's IP, DECnet, XNS, AppleTalk, EcoNet, any of those protocol families, it will in fact accommodate those addresses. The one place that it doesn't accommodate is AF_Unix, because Unix domain sockets are actually very large file name type things. And the address conversion, I mean, back in the old days we used get host by name and get host by address. Those are being converted to get name info and get adder info. Tricky part about these functions is that now we don't get one address, we actually get lots of addresses because we can get the IPv4 address and the IPv6 address in the same call coming back. So we have to kind of figure out which one we're actually looking for here. The ASCII to net, net to ASCII, those have been deprecated. The INET adder function, those are gone, so no dotted quad to a integer kind of things. Those have been replaced with the platform to network and network to platform calls. And this one has just gone completely. So in general, if we use these functions, we'll be able to accommodate both protocol families. So this is the goal. Have one application that's aware of both IPv4 and IPv6, and we don't have to do any conversions back and forth between the protocols. We just simply say, oh, well, this is an IPv4 connection, we'll talk IPv4. This is an IPv6, we'll talk IPv6. It turns out that it's not that hard to do that. Here are the basic structures, Sockaddr in, inaddr, and Sockaddr. Here are their equivalents in IPv6. And there's the Sockaddr storage socket. So let's take a look at a couple of examples here, because I'm going to be running out of time real fast. Here is the socket. This is IPv4. Here is IPv6. So if you just blink your eye really fast, you see the difference between the two protocols. So there's really not that much. If we take a look at the client, there's IPv4, there's IPv6. Now the significant difference here is that this host to net long of the inaddr loopback address got converted to its IPv6 pound-defined equivalent. So there are a couple of cases where the special addresses have special designators in IPv6. But other than that, again, just take the protocol family, stick a 6 on the end of it, and you're pretty much good. SYN6, IFnet 6, etc. The H2 functions, that's where those still exist, but they don't really have much meaning in a 128-bit address. So that's where you get into the protocol, the platform to net conversions and net to platform conversions. So they handle some of that. It's the equivalent of the H2NL and H2NS stuff. So name address translation, this is the getAddr info function. Basically, we pass it in a string, a port, and a potential protocol, and we pass it some flags to tell us we're looking for a numeric host, we're looking for something that's IPv4 mapped. It then returns us a pointer to a structure that has the address information in it. And the address info structures all return the generic sock functions. So they return these guys, SockStorage. So they'll be able to be used for either protocol. So address to name translation goes the other direction. In that one, we're giving it a name, we're giving it an address, and we're looking for its name. So this is the opposite number of the getAddr info calls. Returns the name of the host as looked up by a DNS server out there. So I'll leave you, of course, all these things will be posted, so you'll have an opportunity to kind of go through this. This is an example of doing address resolution. We're saying allow either IPv4 or IPv6. We're looking for a datagram, any IP address, and then we call getAddr info, pass it the name that was passed in as an argument from the command line, and it'll then go out to the resolver to try and figure out where that particular address gets mapped. And this actually shows both examples, both an getAddr info and a getName info example. So I'll leave you this code. You can take a look at it at your leisure. So what's happening here? We had last year, June 8th was World IPv6 Day. And in IPv6 Day, Akamai, Yahoo, Google, many of the government sites all turned up their IPv6 interfaces and tested for the day to see if anything broke. The good news was nothing broke. So all of the infrastructure that had been being put into place over the past several years to support IPv6, because the government mandate for IPv6 actually came out in 2008. So there's actually been quite a bit of work going on over the past several years to support it. They turned it up, it worked. June 6th, 2012 is when everybody is supposed to switch over to IPv6. Now, they're not going to do away with the IPv4. They're going to turn up the IPv6 sides. So we will then officially start every one of the major vendors out there supporting both IPv4 and IPv6. Now the cool thing is, if your machine is capable of doing IPv6, you're going to get a much faster website, because there aren't as many people using that same connection. So you might actually jump on the IPv6 thing right out the bat, just simply because you're going to have some servers to yourself for a while. And that could be a good thing. How do you test whether you've got IPv6 ready to roll? We have the testipv6.com website. You connect to that website, and it runs some tests on your system, and then comes back with a score that says, oh, hey, in my particular case, my IPv4 address was this. I'm running Teredo, which has this header start off. It has a 2001 header. So it says it appears to be Teredo. It then says, hey, there's no problems anticipated because I can actually send packets through the tunnel. If I was forced to go to IPv6, basically, the one concern that they have is that my DNS server on this particular link doesn't appear to support IPv6. So, and that's true, because Cox Communications are a little brain dead. Hopefully they'll get there. They claim they'll be there this year. I hope so. Certainly by June the 6th, I hope so. So, summary. The way you have it right now, we have a circumstance where IPv4 is not going to go away anytime soon. IPv6 is here. It is not a future technology. It's here right now. You've actually had IPv6 support in many of your Linux boxes, your Windows boxes. I mean, Windows XP had IPv6 support. It was almost impossible to get it turned on because it was a horrible registry hack, but it was there. So now that we understand that IPv6 is here, it's now the time for us to start experimenting with IPv6 to guarantee that when we're forced to switch over to IPv6 to talk to particular websites, say in Asia, then we're ready to do so. So by all means, there's a couple of good books, IPv6 Essentials from O'Reilly, and of course, Google is your friend here. You'll be able to find out all kinds of examples of code out on Google. And if you have any questions, contact me and I'll tell you which thing to Google. So fortunately, the conversion to IPv6 is not likely to be a cliff. It's not something that's just going to be suddenly everything stops working. It's going to be a gradual transition over the next several years. But now is the time to start thinking about this, because we have to start rolling forward code and making sure that our code is compatible with both IPv4 and IPv6 as we start hooking up TVs and other such embedded devices with Linux backgrounds inside of them. Okay, thank you very much. Any questions? Yes?
Do you know if like Android or anything will support or supports IPv6?
Yeah, you missed that. Android already has IPv6 in it. Yep. Yeah. Gosh, really?
The question is, what do you think is going to be the breaking point where people are going to say, all right, you know what, I'll actually do it? Do you have any thoughts on that?
Yeah, well, it's really going to be one of those things that I seriously doubt there's going to be a precipitous breaking point. It's going to be we get ready to update the infrastructure for the enterprise, and gee, we can't buy any devices that are IPv4 only. Now, that's been true for a while. I mean, if you take a look at most of the routers that have been sold over the past couple of years, they all support IPv6. And it's just been an issue of the IT departments not willing to turn them on. Now, there is a kind of a hidden gorilla in this room, and that is if you turn on IPv6 but don't turn on the IPv6 security features, now you've just opened a back door into your system. So if you're going to turn on IPv6, make sure you turn on at least the IPv6 tables and implement some of the security mechanisms. Otherwise, you're going to have another channel that many IT people don't understand. They don't know that our good friends at Wireshark actually support decoding IPv6 packets. They never turned it on. As a consequence, there may be traffic going on in your network that you're completely unaware of, because it's flying under the radar of the IPv4 police. So that is a problem, and that's something that, this is another reason why we need to start this conversion process now, so that we understand all the implications, including the security implications. Yeah?
Any idea what the take rate on ISPs for IPv6?
Well, Google, Akamai, of course, is responsible for a lot of the major ones. Oh, the ISPs that serve homes. At this point, I've only been able to get a reading on about half of them, and about half of them that I've looked at will in fact have IPv6 support by June 6th. Cox is iffy. I'm not quite sure. But yeah, it's going to be something that I would suspect that by the end of this year, almost all of the home ISPs will in fact have IPv6 support. Verizon is doing its conversion now. I've been working with the Verizon guys. AT&T is doing their conversion now. They're expected to go, AT&T wireless services are expected to go live with IPv6 this summer. So again, by the end of this year, you will find that most of the carriers, most of the ISPs, the vast majority of the bigger websites will all have IPv6 presence. Yeah? No, actually it turns out that that's one of the key characteristics of IPv6. It actually reduces route table bloat because now so many of the addresses are being assigned to slant 64s or slant 48 addresses, and because of the assignments of relatively large blocks, it actually dramatically reduces the route table bloat. And that's another one of the reasons why so many of the core gateway people are pushing hard on IPv6. There will be a transition where, yes, realize there's no more IPv4 addresses, so the routing table is probably not going to get that much bigger on IPv4. And IPv6 will then be a very small routing table as we start converting major IPv4 chunks over to IPv6. So it actually helps the overall internet by switching to IPv6. Question? Will we have an IPv6 only network? Eventually. But I say, my best guess based on folks that I've talked to is it's probably going to be about 20 years before you'll see that. It just gets to the point where when the IPv4 address support starts to become more trouble than it's worth, somebody will come along and it'll be just like 1981. Okay, tomorrow we're switching to IPv6 and everything drops off. I don't think that's going to happen for another 20 years, but that's just the best guess on my part. Yeah?
Yeah, actually, to that point, because I was working on the e-router specification,
Mm-hmm.
that was put up by Texas, and they are talking about 6 RD and PSI, but it's like way up. Mostly it's close to that.
Yeah, clearly the ISPs don't have as much of a incentive to switch over. They have an existing infrastructure out there, and if they're leasing those DOCSIS boxes, they don't want to have to convert all those things over to V6 support if they can help it. So, that's why I say about half of them will probably have been converted this year because they're already underway and they publicly stated, FiOS has stated this, Cox has stated this, that they're going to be converted this year. Some of the smaller ISPs, maybe not. It might take a little while. Question?
So if you get your home set up and your ISP's IPv6, does that mean you get IPv6 addresses for all your devices in your house that are available on the network, or are you still adding?
You don't have to. You can still run IPv4 in your house and then go to the box that has IPv6 and it has. But if you want to be IPv6, then what happens at this point is that the ISPs are allocated slant 64 blocks. So you could actually then make the argument that it's now not going to be, try to get a static IP address from your home ISP. It's impossible. But when you go to this address space, as they start rolling out IPv6, then they can give you, a slant, a slant 120, and a slant 120 would give you plenty of address space for your house, and you still have now a static IP. The tricky part about that is that now how do you get your IP addresses assigned? And that typically would be through Slack in the router. So you'd have to update your router. You'd have to then basically get your slant 120 or whatever network address, whatever site they were going to assign to you. But yeah, the argument for them not giving you static IPs goes away with IPv6, except for an administrative issue. And of course, they'll charge you more for the static IP. But we know that.
We'll charge you more.
That's right. It won't cost us anything, but we'll charge you more for the privilege. Okay? Yeah, one last question here.
So, kind of speaking about the end consumer and routers in the home, what kind of IPv6 support is there now in consumer level?
In consumer level routing equipment, some of the more modern, I mean, if you've purchased a router in the past couple of years, it typically has IPv6 support in it. Now, the question is, and I haven't seen any of them yet that had DHCP6 support or SLAC support. So the router itself understands how to pass IPv6 traffic. It's the configuration of the IPv6 address space that seems to be lacking at this point. So I suspect that that's going to change in the not too distant future from talking to contacts at places like Cisco and Linksys. So you will start seeing newer equipment that has the ability to support probably DHCP6, because that's going to be the most common thought pattern that the consumer has. They've already set up DHCP in one way or another in many cases. DHCP6 isn't that different.
So is your expectation that these routers at home that have IPv6 support are going to do the 4 to 6 conversion?
There might be a firmware update that would do it.
So you don't expect them to do it today?
I don't think they're going to do it today. So if you want to do IPv6 today, I'd install Teredo. It's an easy way of doing 6 to 4 conversion. I mean, there's several different tunneling protocols. 6 to 4 is one of them. I happen to like Teredo. It's a little easier to administer. But certainly there are at least 3 or 4 of them that are out there that are competing standards, and they all seem to work. Teredo is supported by Windows and Mac OS and Linux. So it's a tunneling protocol.
4 to 6 NAT.
No, it's not a 4 to 6 NAT. There is some argument. People are making the argument for doing a 4 to 6 NAT, but the reality is that they're getting a lot of pushback from the IETF. They really don't want NAT. They want to kill NAT off. NAT has caused so many problems in the internet that it's really not even funny. So they really want to get rid of it. And anything they can do to kill NAT and put a nail in that coffin, they're all for it. So. Mm-hmm.
And, they're basically ready for IPv4, but they're still not ready for IPv6.
Yeah. There's going to be a lot of firmware updates that are floating around in the not too distant future, and of course lots of opportunities for people to brick their boxes and then go buy new ones. And we will then all be able to sell our new equipment. Thank you very much.